In this video, you will review the options for including non-ideal separation calculations in a given process design problem. The two options studied are a direct specification multi-phase carryover for a separator and the calculation of the carryover based on vessel geometry and outlet conditions. The video will also explore how to model an exit device to mitigate carryover of liquids in the vapor phase product from the separator. The aspen hysys separator unit operation assumes perfect phase separation by default. However, it can also be configured to model imperfect separation either by specifying the carryover or calculating carryover using a built-in correlation. This video includes the following tasks. Task 1. Specifying carryover effects. Task 2. Using carryover correlations. Task 3. Adding a secondary separation device. Task 1. Specifying carryover effects. In real-world separators, separation is imperfect. Liquid can become entrained in the gas phase, and each liquid phase may include entrained gas or entrained droplets of the other liquid phase. In many cases, vessel internals are applied to reduce the carryover of entrained liquids or gases. The aspen hysys separator unit operations allow you to directly specify what fraction of each feed phase is entrained in other phases. Product-based specifications are also allowed. These options provide simple methods that can be used to match your hysys simulation results to your design assumptions, a known material balance, or to field data from a real separator. You will begin by looking at phase separation and carryover in the inlet separator in your simulation. Check the vapor fraction of the vapor product stream. You can see here it is ideal separation. The vapor fraction is 1. Now assume that you know that approximately 1,800 kg per hour of light liquid and 3,000 kg per hour of heavy liquid is entrained in the vapor product stream. To apply this, navigate to the Rating tab, select Carryover Setup, and select Product Basis. Change the specification basis to mass, and change the specification to flow. Now set the light liquid in gas to 1,800 and the heavy liquid in gas to 300. To check the result, select Carryover Results. You can see here the fraction of light liquid in gas and heavy liquid in gas. You can also go back and check the vapor fraction of the vapor product stream. As you can see, it is now less than 1. This concludes the first task in our video. Task 2. Using carryover correlations. As an alternative to defining imperfect separation amounts, aspen hysys allows gas and liquid carryover to be calculated by using 3 different calculations. These correlations are the generic, the horizontal vessel, and pro-separator models. All the 3 correlations follow the same basic calculation sequence. First, the program calculates the initial phase dispersion based on the feed flow through an inlet nozzle. All 3 models assume the inlet dispersion follows a Russell-Ramler distribution. After this inlet dispersion is calculated, the calculations calculate the carryover after the primary separation of each phase in every other phase. Finally, based on the separation extent from the previous step, the program calculates the effect of any installed secondary separation device on the liquid carryover into the vapor product. This is only available in the horizontal and the Profess-Pro-separator correlations. In this task, you will explore the Profess-Pro-separator correlation. Go back to the Rating tab. Select Carryover Setup. Select Carryover Model Correlation Based. Set the overall correlation to Profess-Pro-separator. Click View Correlation. Leave the outlet dispersion limits as is, as the Profess correlation will calculate the outlet dispersion without the need for further information. You will not initially have an exit device on this separator. That being the case, go to the vapor exit device and set the mesh pad thickness to 0. Close the correlation window and return to the rating carryover setup form. Now that a correlation has been identified and its preferences and options defined, you can move on to provide the dimensions and other details of your phase-out. Select Dimension Setup. Set the bezel orientation to horizontal. Enter the bezel length. And the diameter. And the light liquid level. You can keep the default sizing information and leave all other inputs empty. Move on by clicking on the Nozzle Setup Radio button. Set the nozzle location for each stream. Now you can check the carryover results from the carryover results form. Here you can see the light liquid in gas fraction and heavy liquid in gas fraction. You can also check the vapor fraction of the vapor product from the Worksheet tab. This concludes the second task in our video. Task 3. Adding a secondary separation device. While the separator studied in the previous task seems to work well enough, your heat exchanger design could be a bit concerned. The LNG 100 LNG exchanger brings in the outlet separator vapor stream as its hot side outlet. Based on your correlation-based real separator calculations, significant flow of liquid droplets will feed into the exchanger. Your exchanger design is concerned about these droplets and their effect at high velocities. You need to look into using some kind of secondary separation device, such as mesh pad, vane pad, to try and to knock out these liquid droplets. Your target is to remove 99% of all liquid droplets from 50 to 55 microns in diameter. Open the Rating tab. Select Carryover Setup. Select the Correlation Setup. Click View Correlation. Set the mesh pad thickness to 100 mm. Now check the Results tab. Select Vapor Exit Device and also check the exit device efficiency. As you can see, the efficiency of removing droplets with diameter of 50 to 55 microns is more than 99%. This is for the light component and the same for the heavy component. This concludes the last task in our video. Thank you for watching.